I'm going to try to go through M15 very quickly, and I'm using my ID, so the ordering of the questions may be slightly different. So let's get started. The first question is the mixed strategy question. So we have the diagram already, but I'm going to try to draw the diagram from scratch because as we discussed during the discussion earlier on Friday, I said if I give you the same question on the final exam, I may not give you the diagram. So you may need to draw the diagram yourself. I haven't decided that yet, but basically you need to be able to draw the diagram yourself if you see a question like this. In any case, let's get started with drawing the best response for, say, the role player. So for the role player, the best response is a function of the other player's action, which means the column player's action. And the column player is playing L with probability Q, and R was probably 1 minus Q. So basically, it's the best response of Q. So the action is parameterized by Q. And there are three possibilities. One is I'm always going to play U, I'm always going to play D, and I don't care. So I'm going to say I'm playing U with probability P, and I'm playing D with probability 1 minus P. So we're going to write the best response as a function of P. I mean, not as a function of P, but in terms of P. So the result will be P as a function of Q. So what's the best response? Best response means when do I prefer playing U? So let's set up an inequality that says the expected value from playing U is larger than the expected value from playing D, not R. So if I play U, I'll get either 0 or 4, and I'll get 0 with probably Q, and 4 with probably 1 minus Q. So the expected value is 0 times Q plus 4 times 1 minus Q. And if I play D, I'll get 6 with probability Q and 0 with probability 1 minus Q. So we can simplify this. This becomes, I think, is Q is less than 0.4. So when Q is less than 0.4, it means I'm going to always play U. And if we want to express always play U in terms of P, we just write 1. Because P is probability of playing U. If P is 1, then I'm always playing U. So when Q is equal to 0.4, then the value I get from U and D, they're the same, so I don't care. So any way I mix is okay. I can play U and D with any probability because I get the same value from both of them. So when Q is less than, or I mean Q is larger than 0.4, then I'm going to play always D, which is 0 here. Okay, so that's our blue best response, and let's check if the drawing is correct. So one thing that's really bad about the drawing is we have left on the left and right on the right. So left means Q is 1. So remember, Q is the probability of playing L. So this is Q is 1, this is Q is 0. So it's actually going the other way. So the Q is getting larger when getting closer to the origin. But in any case, this will be slightly less than 0.5, so it's actually 0.4. So we know that this value is actually Q is 0.4. When Q is exactly 0.4, I don't care whether I play U or D, so anything in between is okay. So that's what this vertical line means. And if Q is between 0 and 0.4, so if Q is less than 0.4, I'm going to best respond by always playing U. So this is always playing U, so that's why we have a horizontal line here. If the number here is 0 instead of 1, then we should have a horizontal line there instead, but we don't have that. So at the end, when Q is larger than 0.4, we always play D, so that's why we have the best response that's always playing D. So that's why we have a best response function like this. Okay, so we can probably draw the other one the same way. That's the best response of the column player, and it should be a function of P, and it's written in terms of Q star. So let's see. We're going to use the same approach. We're going to check when L is larger than R. if I play L, I'll get 7 and 7. 7 was probably P, and 7 was probably 1 minus P, so it's basically just 7. And if I play R, I'll get 0 was probably P, and 7 was probably 1 minus P. So we have the comparison again. That basically says P is larger than 0, right? So when P is 0, then we have 7 on both sides, so I don't care how I mix, so I'm going to mix any way I like. If P is strictly larger than 0, then 7 is strictly larger than whatever that is. So I'm always going to play L, and playing L means Q is 1, because Q is probability of playing L. Okay, so let's draw the best response. So first, when P is 0 means I'm playing U with probability 0, means I'm always playing, always playing D. So when I'm always playing D, then my best response is anything. So again, we have kind of a vertical line, vertical relative to the vertical axis. So we have a horizontal line here that says, if the other player is playing D, I don't care how I mix. I can do anything I want. And if P is larger than 0, which is the rest, I'm going to best respond by playing L for sure. So here, this is L, so we have a vertical line here. I'm always playing L. So similarly, if I have 0 instead, then we should have a vertical line here on top of R, because then I'll always play R. But here we don't have this, so let's get rid of the confusing stuff. Okay, so now we have the diagram. And by definition, Nash equilibria are the equilibrium points where we have mutual best responses. So in this region, where the red curve and blue curve coincide, then it means in this region, Q is the best response for P, and P is also a best response for Q. So by definition, this region is the set of Nash equilibria. And since we have the complete best response function, we have all possible Nash equilibria here. So the only thing left is just to write it down. And in this region, the row player is always playing D, and the column player is playing L with probability Q. We write it with L with subscript bracket Q, and R with probability 1 minus Q, and we need the restriction that Q is in between 0.4 and 1. And the question, I think, is asking us for the smallest and largest value, so 0.4 to 1. Okay. So moving on to the next question. So last year, in the previous 2 years, I actually played this name game during the lecture. This year, we didn't have time to do this. So if I put something like this on the exam, it will not be in the name game. It's probably going to be something similar, but not this, because you haven't seen like the strategy to win these kind of games. But I will go through it anyways, because as I said, we may have something similar. The way to solve these kinds of n can be, so there are arbitrary number of rounds, kind of sequential game. It's the same. You just start with n is 1, n is 2, and maybe 3 and 4, and try to look for the pattern and try to reduce the larger n games to a smaller n game. So the idea is the same, but I'm going to say that we're not going to have like exactly these kind of name games on the exam. And also, if you don't know the strategy, it's hard to come up with the strategy actually for these questions. So they are actually kind of hard. Okay, so let's get started with the n equals to 1 case. And when n is 1, we have 1, 1. So obviously, the first player will win. Right? So the first player can just take 1 from each pile, then the first player wins. So when n is 2 and 2, so there are 2 possibilities. One is the first player can take 1 stick from each pile, then it just becomes the 1-1 game, and in that game the first player wins, and the first player in the 1-1 game is the second player in the 2-2 game. So in that case, the second player wins. However, there is another possibility. The first player always wants to win, so he or she will try to win. So he or she may want to make it 2-1 or 1-2. But it really doesn't matter because the second player will just take out that 1, so it becomes 2-0. So when we hit 2-0, that means the first player can only take 1 from the first pile, making it 1-0. So the second player will just take the remaining stick and win. So in this case, the second player would win as well. So basically, no matter what the first player does in the first round, it always gets converted to something where the second player will win. So when n is 2, the second player will win. And I guess we haven't seen the pattern yet, so we'll continue. So when n is 3, we have 3 and 3. So the trick here is the first player wants to win, so the first player can choose to convert the game into a 2-2 game. So suppose I'm the first player. Then I can just take away 1 stick from each pile. It becomes a 2-2 game, and we already know that in the 2-2 game, the second player wins. But I'm the first player in the 3-3 game. So it means I'm also the second player in the 2-2 game if I move first to make it 2-2. So that's why I will just always take away 1 stick from each pile to make it into a game that I will always win. So I'll win that way. So that's why first player can always win. So that's n is 3. So you can probably guess what will happen in 4-4 now. So the first player, there are 2 options. One is making a 3-3. In that case, the first player in 3-3 game, which is the second player in the 4-4 game, will win. So that's not good for me. So as the first player, I may want to do something else. It turns out it won't help me. So I may want to convert it to, say, 4 and 3, or 3 and 4. They're symmetric, so it doesn't matter. But then the second player can just take away 1, so it becomes 2 and 4. So when we get to even number of sticks in each pile, no matter what one player does, the second player can always respond by taking away the remaining odd numbered stick, the piles with odd numbered sticks. So for example, if say the first player makes a 3 and 2, I can just take a 1 to make it 2 and 2, which I will win again. And if I make it 3 and 1, then I will take away 1 from each pile to make it 2 and 0, which here I will win as well. So it doesn't matter what the first player does, the second player would win in all of these cases. So that would be why second player always wins. Okay, so now we are finally getting to n is 5. We can probably stop here because we can see that when n is 1-3, first player wins, and when it's 2-4, second player wins. But let's say 5, we get to 5 and 5. I want the first player to win, and there's actually a strategy, just convert this to 4 and 4. In the 4-4 game, we already talked about 4 and 4. The second player always wins. And in the 4-4 game, in the 5-5 game, when we convert it to 4-4, the first player is actually the second player there. So the first player will always win. There's a winning strategy. So basically, to summarize this, when n is even, then the second player always wins, so the value is -1. And when n is odd, then the first player has a winning strategy. So the answer here, when n is 5, is 1. All right, so moving on to the next one. So the question here is asking us to minimize the distance from, say, a bus stop, let's say x, to 7 plus 5 plus 3. So there is actually a trick to do this. So the solution to all of these is just x is equal to the median of these numbers. But I think the question is not asking you whether you know the trick or not. here is 5. It's asking you to actually search over all possible integer values and see which one results in the largest one. So there are like 5 obvious candidates. So the way to do it is just to try all possibilities. Like it can be 5, 4, 6, 3, 4, 5, 6, and 7. So the way to do this, so the slower way, and the way that you for sure you'll find an answer is just try all of these numbers and see which one leads to the smallest minimum value. I think it will turn out to be 5, and you can just put 5 in. Okay. So next question is the search question. So we have player, actually not a player, it's just person A, Alice, has 4 friends, and each of her friends has 4 friends, and each of her friends' has 4 friends, and one of these people, so we have basically a large tree here, one of these people is B, Bob. So here we are asking about the luckiest case. So there are 2 possibilities, 2 versions of this question. One is asking for the best case, one is asking for the worst case. So it doesn't matter which algorithm you use, BFS, DFS, or IDS. The best case is always B is the first one that we search in the new level, and that's the best case. And the worst case is always the last one in the current level. So here we're asking for the luckiest case, and if the question is asking about BFS, we need to search everything, and here we are asked to use DFS, so I'm going to search the leftmost, and then we already see the goal. So we search 1, 2, 3, and 4. So that's why the answer is 4. Okay, so the next question is the vaccination question. So I had this vaccination question last year on the final exam, and at that time I think whether or not to take the vaccine is not a very political issue, and now it becomes a very political issue. So I don't want to. So I want to clarify here that we are just having a game theory discussion about vaccination. It has nothing to do with the COVID vaccine. So it's not a question about convincing you whether to take the vaccine or not to take the current COVID vaccine. Okay, so let's just talk about game theory. So there are 160 people in total, and there are n of them who are unvaccinated. So let's suppose there are n people unvaccinated in equilibrium. So being in equilibrium means everyone is best responding. So for those n people who are not vaccinated, they must be best responding. So in equilibrium. So for those n players that are unvaccinated, we must have staying unvaccinated should be at least weekly larger, would at least have a weekly larger expected payoff. There are no randomness, so strictly a weekly larger payoff compared to getting the vaccine. So I'll actually use N to say not vaccinated and V to represent vaccinated. So if I do not take the vaccine, then I will get payoff or value N over N. And if I take the vaccine, then we're assuming there are N players who are not vaccinated. If one of them, if I, being one of the unvaccinated people, I choose to take the vaccine, then the total number of unvaccinated people would be decrease by 1. So the value here is actually not this thing. It's n minus 1. So that's the key thing here. So if we are just solving them like this is larger than that, and the other one is also larger than this, then we don't have a solution. But the reason why we have a solution is because if I switch, I'm going to decrease the total number of unvaccinated people by 1. So that one is basically me. And because I switched from unvaxxed to vaxxed. So that's why there's a -1 here. So we're going to use the same trick for the remaining n minus n players. So these people are vaccinated. So they should prefer getting vaccinated compared to not getting vaccinated. So if I get vaccinated, there will be a cost. And let's see. So this number should be larger than if I stay not vaccinated. Then because I am one of these n minus n players who are vaccinated, if I actually switch and choose not to vaccinate, then I'm actually adding 1 to the group of unvaccinated people. So again, here, that's actually the key point here. This is, again, is me because I switched from vaccinated to not vaccinated. So now we have 2 equations and 2 unknowns. We know the values of alpha, beta, and c. So we know all of these numbers. We have 2 inequalities, and then we can solve these. So I guess I will not spend time solving these 2 inequalities. You can just plug in the numbers. You have 2 inequalities, and then you'll get n is in between 2 numbers. And usually there is only 1 integer that's between these 2 numbers. Sometimes, in a very rare case, both of these happens to be integers. Then you have 2 possible answers. In most of the cases, n is just in between 2 non-integers. So you just pick that integer that's in between. Okay, so let's move on to the next one. So it's a mixed strategy game again. It's the Battle of Sexes game, not Batman or Superman or something like that. But well, anyways, and B and S can also stand for Bach and Stravinsky. I told the story during the lecture, so I'll not repeat it here. So we're going to assume whose value are we asked to find? The column player. So I will assume the column player is playing B with probability Q and S with probability 1 minus Q. So I think we only need to assume this. So in order for the player to mix, in order for the role player to mix, then the role player should equate the action B from the action S. So basically, if I play B, then I should get the same value as if I play S. Let's actually assume the probability of playing, so the role player of playing B is P, and playing S is 1 minus P. And we can solve this equality for the column player. So if I play B, then I will get 3 with probability P and 0 with probability 1 minus P. So that's 3P plus 0, 1 minus P. And if I play S, I will get 0 with probability P plus 4 with probability 1 minus P. So that's actually the value, for me, expected value of the whole game when we have a mixed strategy equilibrium. So we can actually solve for P here and plug P back in, and then we can get the value. So that simplifies the problem of first solve the equilibrium and then plug everything in. So I will solve it here, and I think that this is 4/7, right? And then you can put this P is 4/7 back into these two expressions, and on the left hand side it will be 12/7. On the right hand side it will also be 12/7. So it doesn't matter how I mix between Q and 1 minus Q. I always get 12/7. So that's why that's actually my expected value. So if you do want to spend the time to solve Q and 1 minus Q, at the end you can get some number for Q and some number for 1 minus Q. And when you compute the expected value, you can do Q times 12/7 plus 1 minus Q times 12/7. Since these two numbers are the same, so the total expected value in the equilibrium would still be 12/7. So basically you can save yourself some time by solving only the probability for one player, for the player that you are not asking for the expected value. So that's the trick here, and let's move to the next question. So we start with a configuration of lights like this, and every time we're just flipping to adjacent lights. Yes. So we are just effectively we're moving this one to the left or to the right. We never actually want to move to the right, but we are moving to the left by one position every time. So you can probably guess how I'm going to move this. I'm going to move this one. Probably I will never move this one to somewhere else other than just to this rightmost one here, because moving this one to some other position means I'm going to switch between two ones, and it's a complete waste of step. And we're asking for the smallest number of steps, so we don't want to waste those steps. And then we're going to move this one to here, and I guess you can see the pattern. So how many times do I need to move? So first, we should just count the number of zeros on the right. So for the first one here, I just move 2 steps. For the second one here, note that after I'm done with the first one, all the 3 zeros will be on the left of that one, so I need to move 3 steps. I need to switch between the 3 zeros, so I'm going to add 3. And that actually holds for all of these ones. I'm just going to move the number of steps we need to move. It's just the number of zeros on the right. So that's why there are 3 zeros on the right of this. So we add another 3. There are 4 zeros on the right of this, and there are 5 zeros on the right of that one. So that's the answer of how many steps we need to move the one to basically flip. Okay. Moving on to the next one, and the question is, we can have any shape we want, and we need to search through everything. So we want to minimize the number of steps for IDS. So for BFS and DFS, it doesn't matter. I just search through all the states once. It doesn't matter what the shape is. For IDS, if the tree is kind of tall, then we need to search the smaller tree with steps limit 1, with steps limit 2, with steps limit 3, and so on. So there are a lot of ways of repeating the same thing. So if we can make the tree as shallow as possible, then we will reduce the number of nodes that are searched. So the shallowest possible one is not having multiple roots, it's having one root, and everything else is a leaf. So you have basically 162 leaves and 1 root. So then the question is, with IDS, how many nodes do we need to search? So we need to search the node once, and then we need to search the depth 1 tree, which is everything. So it's just 1 is the first iteration, and 163 searching through everything using the FS. in the second iteration. Okay. So the next question is asking about projected variance. So we need to project and then take the variance. So first, let's do the projection. So first, let's project this thing onto the principal component 1, 0, 0. So remember, if this is a unit vector, then projection is basically just the dot product, so x transpose u. If it's not, there is a more complicated formula, but you can always just make this into a unit vector. So if it's 2, 0, 0, you can make it 1, 0, 0. If it's something else, you just divide it by the length. But in any case, after we make it a unit vector, we just do the dot product, which means the x1 is 3, and x2 happens to be 3 as well. So immediately you know the variance is 0, but we should still try the formula. So mu here is the average. So there are 2 points, so it's half x1 plus x2. So it's half of 3 plus 3, so it's 3. And sigma square would be 1 over 2. And here we are assuming we do not subtract 1 from the variance, so we're not using the sample variance. And we need the sum, so x1 minus mu squared plus x2 minus mu squared. So we know this is 0, this is 0 because x1 and x2, they're both 3, so the whole thing becomes 0. Okay. So the next question, we have a table, but that table is actually not on the gaming matrix, because the total payoff is actually whatever is in the table plus the value of slacking. So the first step is actually to add the value as is 5 to the table, so that the table is actually the game matrix. So when do I add 5? So if A slacks, then I'm going to add 5 here. If B slacks, I'm going to add 5 here, and I'm going to add 5 here and here. So now we get the actual table, and then we can figure out when would this be a Nash equilibrium. So the condition for something being in a Nash equilibrium is we have mutual best responses. So this should be a best response, and this should be a best response. So when is X a best response is when, given the other player is working hard, then I'm going to prefer working hard compared to slack. So I'm going to say X should be larger than or equal to 2 plus 5. That's the condition when this is a best response. And similarly, when is this a best response? So it means when A is working hard, why would B work hard? So that's when working hard is better than slacking, which gives you the same condition. So the question is asking for the smallest value, so that value is 7. Okay, so moving on to the next question, and we have a game tree like this, and you have all the probabilities, and it's labeled which players are min players and which players are max players. So when you see a min player, I just take the minimum, so that's the one we take, and min player, I'm going to take the minimum, min player, take the minimum, take the minimum. And then when there's a chance, the chance player does not do anything, just take the expected value or the weighted average of these two values so that I can get something here. So that's basically the expected value between 0 and minus 5. So 0.95 times minus 5. So that's what the max player will get if the max player choose the left branch. And similarly, if the max player chooses the right branch, then the max player will get either -9 or -9, so it doesn't matter, it's just -9. So the max player is going to pick the max between the two. Which one is the max? Obviously this one, because it's something less than 1 multiplied by -5. This is just -9. So the max player will pick this, and the question is asking for the expected value. So when I say expected value, if I don't specify for which player, it automatically means the max player. And if I don't specify which player are these values for, again, it means it's for the max player. So basically, in this case, the mean player would get -3, but I'm not going to write those down. In any case, the max between the two is just that. Okay, question 12. I think we went through something similar during the lectures. So it's basically are we doing BFS? Yeah. So we have state 1, 2, and 3, and 4 and 5. And if you write down the first few levels, you can see the pattern. This is 8, this is 16, and basically will be 2 to the power something. And 251 is 2 to the power 9. So if we are using BFS, then it means we need to search this, everything, the first level, second level, and so on. So we need to search through everything. And that 2 to the power 9 is actually the first node in that level. So we're not going to search any of the remaining stuff. So we're going to search everything, basically. So that's why it's for 512. 512, sorry. If the question is asking about DFS, then we only need to go through, I think, 10 nodes. Okay. The next question is about rearranging the nodes so that we can prune as much as possible. So let's first solve the game. So the max player is picking the max. So the max between the three, the max of the 3 is 5, the max of these 3 is 3, and the max of these 3 is -3. And the mean player is picking the minimum, so the mean player will pick this. So we should probably search this branch first. So I'm going to label this one first. The first subtree of any internal node must be searched. So we cannot prune them. So we won't be able to prune these 3. And for the same reason, we need to search at least one of these nodes in the remaining branches, so we can prune for any number you have. We can prune at most 4. So we only need to figure out among those 4, for possible ones, how many can we prune. So let's start with the first branch. So we'll search the first branch and we'll get the value here as -3. So for the mean player, I know that I'm going to get at least -3. So I can get something smaller, but at least I can get -3. So I'll actually say at most I will get -3, but well, it sounds weird. But so I can get something better than -3 basically for the mean player. So basically, if the mean player search this branch next, then for example, if the mean player searches this branch first, after searching the second branch, then I'm going to see that the max player will pick the max among all of them. So actually, so the max is 7, not 3, sorry. So I will search this one first. So the max player will get 7, and it turns out I'll get something larger than or equal to 7. So for the mean player, I can already get something less than -3, I don't really care how much larger than 7 do I get, so I'm not going to worry about the rest of the tree. So if I do that, then I'm going to prune both of the nodes here. So if you consider the alternative, if we actually search this one first, then I only know that the max player will get something larger than or equal to -9. So for the min player at the top, it's actually possible for me to get something like between -9 and -3. So I still want to keep searching. So in that way, I cannot prune both of the nodes. So that's not a good choice if we want to prune as much as possible. So I'm going to start with this, and I'll get 7. So I know I'll get larger than or equal to 7. Then the remaining 2 will be pruned. And you can probably get the pattern here. I'm going to search this 3 next, and I'm going to search this one in the middle first. So I know I'm getting at least 5, and the main player knows that he or she is already getting something less than -3, so I'm going to prune the rest. So the same thing would happen if I search -5 first. I won't be able to prune as much as possible. So here, we actually pruned 4, and we said we can prune at most 4, so we're done. So that's the answer 4. Okay, now moving on to the last question. So in the homework, we did the 2D version. So in 2D, we basically had a plane, and there's one corner of the plane that's the minimum. And we know, since it's a plane, if we do any kind of local search or the hill climbing search, if we start anywhere, we'll just go down the hill, and it will always get to one of these 4 points, whichever one result in the smallest value. So in 3D, it's the same thing. It's just, it looks slightly more complicated. It looks like a cube. So you can probably see that there is one corner that has the smallest value, and we are minimizing. So no matter where you start, you're just going to go down to that point. So it turns out we only need to figure out among the 8 corners, we know the values of those 8 corners, and which one results in the smallest value of the score. So if you look at this, we probably want I to be as small as possible, we want J to be as large as possible, and we want K to be as small as possible. If all of them hold at the same time, then this number will be as small as possible. So I'm going to pick the smallest I, largest J, and smallest K. So it turns out that's the combination that will result in the minimum point here. And again, it doesn't matter where we start, since I think it's easier to visualize on the plane. No matter where we start, if we do hill climbing, we will always go like in the direction of the global minimum, and the global minimum is one of the corners.